Okay, in the last lecture, we started talking about the idea of steady state error. Now, this is an additional way that we need to look at the systems in many cases. Up to this point, we've been focusing primarily on the transient response of the system, looking at getting the system to go to the set point as quickly and as efficiently as we can. And we've been focusing on using a test case for that as a step input. And so that is a real and valid and very applicable thing that we need to look at in our look at control systems. But another thing that we need to look at, as we mentioned last time, is the idea of steady state error. Once we get the signal or get the system to the set point or near the set point, is it going to stay on that set point, or is it going to fall shy of it? Is it going to drift around on that set point, or is it going to lock on to that set point and stay right on it? And this we call steady state error. We want to minimize the steady state error in many cases, and in some cases that's the primary function of the controller, is to maintain a set point or minimize a steady state error. So we want to enter into that discussion, continue on. Let's put a little theory behind it today, see if we can understand it a little bit better than just the hand waving that I did last time. So I want to see if I can do this, and my system is locked up, so I can't move it anymore. Let me close it down real quickly here, and we'll start it back up again and see if we can get this. Okay, there we go. All right, so we've got steady state error in here. Now, before we start on the theory of this, we need to back up just a little bit and revisit some of the things that we looked at very early in the semester. As you know at this point and are well acquainted, that our test case that we've been using through the primary work through this semester has been the step input, and the Laplace transform for that, which we haven't used a whole lot, but it's there nonetheless, understood, is a 1 over s. Now, in steady state error analysis, we need to expand our test case from a step input to include other types of input, because the response, the steady state error in response to a step, is different than it is to a ramp and is different to a parabola. And so we need to look at this, because these are typical kinds of inputs that we find for systems that we're looking at maintaining a zero steady state error. For example, an oven, a commercial oven for industrial processes, you might want to ramp up to a certain temperature, maintain a steady state value, and then ramp down. Cooling it or heating it at a certain rate and then cooling it at a certain rate is very important, and so that you don't destroy the part. And so ramp is a big deal. Make sure it stays on that step, or on that steady state error as you want it to. So we're going to expand that. Remember, ramp 1 over s squared, parabola 1 over s cubed. So have that kind of in the back of your mind as we go forward through this analysis, because we're going to need it in the general case for sure. So as we move through this, let's take a typical system. We've got a feedback system. We've got an open loop system here of G, and we've got an input of R, an output of C, and we're generating an error, and we're going to call that E. And so now remember, because it's going to come up in this analysis, what we're going to do is the E is generated by the subtracting the output from the input. Okay, just a little note there that we're going to need. So here comes some analysis, and it's mainly just rearranging and a little bit of algebra. We can write the closed loop transfer function using our block diagram algebra, which is G over 1 plus GH. Nothing too surprising there. We've all done that many, many times. Now, we can find the output of of this block diagram, the C, by multiplying the input times our closed loop transfer function, and we expand that out and we end up with R over G, or R times G divided by 1 plus G. Now, to generate our error, which is what we're going for, remember, we're trying to find steady state error, and so we're writing an equation that describes the error in terms of our block diagram parameters. And so error is going to be, just doing a little bit of substitution in here, our error is going to be our output, our input minus our output, like we discussed up here, right? The output minus the input. And so we just write that a little equation in there, and then we can expand those and expand our C into an R times T, and then ultimately we end up with this equation, which we then can rewrite into our describing our error in terms of our input divided by 1 plus GS. That's where we finally end up at. Okay? All right, so now we have an equation that describes the error in terms of our input and our open loop transfer function. Okay, so that's a nice form that we like. So then we ask ourselves, what happens when when time goes to infinity? What is the error associated with that when time goes to infinity? Well, we are going to be using the final value theorem. Remember, the final value theorem said that the limit as t goes to infinity for x of t, the function of t, is going to be equal to the limit as s goes to 0 of s times the function in the s domain. Okay, that was the final value theorem. And so we have the final value theorem here. And so that's what we're going to employ here to solve this this equation for us. So we look at our final value theorem and substitute that in, and what we end up with then is this equation where the error at time is equal to infinity is equal to the limit as s goes to 0 of s times the input divided by 1 over gs. So this is a good and general equation. This is the equation we're going to be using to develop all the rest of this analysis. Okay. Now we're going to shortcut this a little bit, but for now let's just play around with this equation just a little bit and see what we kind of output we can get with it. So let's imagine a test case here. Or a case where we have G is equal to 30 S plus 10. Okay, just a typical open loop transfer function, and let's subject that to a ramp input and ask the question, what is the E at infinity for this? Okay, what is the error at steady state for this? Well, we can do this. We can say that E at infinity is equal to the limit, I'm just rewriting this equation, as s goes to 0, s r, and in this case our r is a ramp input, so that's going to be 1 over s squared. We talked about that just a minute ago. And then we're going to have 1 over 1 plus our g, and our g in this case is just 30 over s plus 10. Okay, so that's our equation that we need to solve to find out what this error is. And so let's do a little bit of playing with this. The limit as s goes to 0, and I'm going to multiply this through that and end up with a 1 over s, which I'm going to take and multiply down through the bottom, s times 30 s and s plus 10 Okay, and I can drop these two out and end up then taking the limit of that as s goes to 0. What I end up with is 1 over 0 plus 30 divided by 10. Okay. Rearranging that just a little bit, dropping this out, inverting, I end up with 1/3 is equal to the e to the infinity. Okay, and so what we find out is that we have a finite error, steady state error, associated with this transfer function with a ramp input. Okay, it would not snug up to the step input. We would always have a finite error associated with this system. So that's the application. That's how we're going to use it. And this is the general case, and this is the general equation that we are going to be using to look at some more specific cases and develop a more intuitive feel for what we're doing and how we're going to do it and how we're going to design with this. Okay, so general equation and the application of that.